Hello, my name is Rohan, and I'm one of the undergraduate tutors. In this video, I'll be talking to you about the three different definitions of entropy. This is really important on this coming midterm, and it's not really something that you can just copy off your cheat sheet. It's really important to understand when each definition applies and what are the limitations of each definition. And I really think a trick to succeeding on this test is really understanding the fundamentals of these definitions. And then in a following video, I'll talk to you about the difference between total entropy calculations and molecular molar entropy calculations. When I took this class, I felt like a lot of the points I lost were just kind of careless mistakes in the difference between molecular and molar entropy and total entropy. So to start off, the three definitions of entropy that we learned in this class are the thermodynamic definition. We also learn the statistical definition, and the probabilistic definition. So first, the thermodynamic definition is defined as delta S equals Q reversible over T. And to get an idea of the situation we're talking about here, I'll draw a picture. We have two systems, A and B. And system A and B are exchanging heat. The way I drew Q is defined as heat leaving A and heat entering B. Eventually, the system reaches thermal equilibrium. A will become A prime, and B will become B prime. And because they're now at equilibrium, there's no longer any net heat transfer. So if we wanted to talk about the change in entropy in A to A prime, or B to B prime, we could use the thermodynamic definition of entropy. And it would follow just as the of the Q reversible, the heat transferred over the temperature. An important caveat of this definition is that the Q we're talking about must be reversible. The heat transfer must be a reversible heat transfer. And this makes sense. Reversible heat transfer just means that you can account for all the heat that transfers from system A to B. In real life, some heat would be lost to the surroundings. And if you don't know, if the heat transferred is, if some heat is lost to the surroundings, the entropy calculation you get from this definition will be incorrect. So when you apply the thermodynamic definition of entropy, the heat transfer, or Q, must be reversible. Okay. Moving forward, the statistical definition of entropy is defined as S equals the Boltzmann constant times the natural log of W, where W is the multiplicity. And in this class, there are two multiplicities that we discuss: configurational and energetic. So for configurational, it's best to think of some container that's divided up into M boxes. And within the container, we have N particles. So N particles distributed within those M boxes. And if I wanted to calculate the multiplicity of the situation, it is defined as M choose N, which follows this formula: M factorial over N factorial divided by M minus N factorial. Okay. That's configurational entropy, or configurational multiplicity. For energetic multiplicity, we should think of the example of multiple energy levels like this. And we have n particles, n total particles. Now these particles are distributed among the energy levels, and we have little n sub I particles per energy level I. So that would mean N0 or N1 here would be 4, N2 would be 2, N3 would be 3, N4 would be 2, for example. And if I wanted to calculate the multiplicity of this system, it is just n factorial, big N factorial, over N1 factorial times N2 factorial, dot, dot, dot. So the total number of particles factorial divided by the factorial of the number of particles in every energy level. Okay. So these are two different measures of multiplicity, and they each have their own measure of entropy. The configurational measure of multiplicity has a configurational entropy, and the energetic measure of multiplicity has an energetic multiplicity. You can think of the multiplicity as a probability or description probability. And configurational multiplicity and energetic multiplicity are independent. Therefore, if I wanted to talk about the total multiplicity, that's just defined as the configurational multiplicity times the energetic multiplicity. Now, because the statistical definition, the statistical entropy is a logarithmic relation to the multiplicity, we know that if the total multiplicity is the product of the configurational energetic multiplicity, the total entropy then is the sum of the configurational entropy and the energetic entropy. Okay, great. Now, for the thermodynamic definition, I pointed out that the Q, the heat transfer, must be reversible. And you'd think there might be a caveat for the statistical definition as well. But actually, the statistical definition is pretty fundamental in thermodynamics. And it's true in pretty much every situation. If you can calculate it, this calculation of S will be accurate. But the issue is, this is a very mathematically intensive way of calculating entropy, and it may not always be convenient. Moreover, if you have a very large value of n, these factorials you have to calculate, you might not be able to calculate them with a calculator. So this may be computationally intensive. Computationally intensive for large n. Okay. Now you might ask yourself, so if you have large n, and you can't talk about reversible heat transfer, how can you calculate entropy? That's where the probabilistic definition comes in. The probabilistic definition is defined as negative n, number of particles, times k Boltzmann, times the sum of pi natural log pi. And this isn't really a unique definition of entropy. Really, the probabilistic definition of entropy is the statistical definition of entropy, but for large n. So when you have sufficiently large n, you can apply Stirling's approximation. And when you apply Stirling's approximation to the statistical definition of entropy, you get the probabilistic definition of entropy. So, obviously, that will create a very important condition for the probabilistic definition of entropy. You must have large n. Must have large n. Okay. So now, when you're taking your midterm, or when you're supplying this in any kind of thermodynamical situation, it's important to understand what information is given to you and what the conditions of the problem are. If you have a system where you're calculating heat transfer, then it makes sense to use the thermodynamic definition if the heat transfer is reversible. If you have a system where you can catalog the position of a particle at any point, which is the configurational entropy, or you given the energy levels of all the particles, and you do not have a large number of n, it's easy to calculate. The statistical definition is a good option. If, however, you have a very large number of n, but you can still calculate the probability p sub I for every energy level, you can use the probabilistic definition.